I'm actually going to jump in. Oh, I'm not going to jump in. I hit the play button again. This is also new.
There's always a mess up the presentation button.
Yes, yes. I'm going to jump right in and talk about something from the middle of my slides. But I'm going to talk about this first because this is the thing that sort of inspired this talk. So we have a single optimization pass inside Chez scheme, which the nanopass system makes easy, that looks for a pattern that looks like this, which we call predicate in value context. And so it looks for this big if expression where all of the leaves of this if expression are true or false. And it generates extra code around it in order to optimize it. Now you might wonder, how is this an optimization? You just generated more code. But it turns out that it is an optimization because somewhere later in the compiler, where we actually take care of these things, we no longer have to generate no longer need to manifest all the trues and falses in our output code. We only manifest one true and false. So if we had not done this, we'd have assembly code that looked kind of like this, and we've got true and alt2 here that only generates our false, and another generation that only generates our false down here towards the end. But when we do this, even though we added code, we end up with less assembly code coming out of this because we only have our true end and our false end, and all of the stuff that we move from value context into predicate context now is just what Kent likes to refer to as traffic cops that are basically saying go this way or go that way. The only kind of downside of this particular optimization is that it's sort of pattern-based. So it's specifically looking for trues and falses down here. It's specifically looking for this kind of complicated if nesting. If anything else happens down here, it just has to give up. And you could imagine that if this only returns two different values, even if they didn't necessarily correspond exactly to true and false, you could extract those values. And maybe even if it had more than two values, but it was manifesting them more than once, it would make sense to extract it. So with that, what I'm going to talk about today is sort of some of the clever representations and small optimizations that we do inside Chez scheme. And so I'm currently at Cisco Systems. I work with Kent Divvig, who's one of the other maintainers. And we have two other maintainers, Oscar Waddell and Bob Berger, who are also employed on products that work on Chez scheme and do their maintenance in the spare time like Kent and I do. The other thing is I like to think of this as sweating the small stuff. So this is worrying about all of the little stuff inside the system and order to have a fast overall system. So I'm going to start out talking about representations. And let's just start from what's the basic thing that our representations have to do. So we're in a dynamically typed language. We can't just store the value that we need. We need to store some type information about the value as well. And so the way that lots of systems approach this is they just use a machine word, one single machine word to represent every object in the system. And so with the machine word, you can always bail and go to a pointer that points off to all the information you could ever possibly need about this thing. And we do something similar. Now, on a 64-bit machine, that's going to be 8 bytes. And on a 32-bit machine, that's going to be 4 bytes. And so we also need to think about what are these things pointing at, and what is the alignment we care about for the things that we're pointing at. So the largest thing that we ever want to represent in the heap is our floating point representation, which is a 64-bit IEEE floating point number. And so we end up with this very nice 64-bit alignment where we have 2 scheme objects could be stored in that space, or 1 flow num. And here, just 1 flow num or 1 scheme object. And you'll notice, which I've sort of highlighted in red, which you can maybe see, the bottom here goes 0, 8, 0, 8, or I guess I practice this on the not wide ones. I guess it goes 8, 0, 8, 0 because there's more space on here. And which corresponds in binary to 1, 0, 0, or 0, 0, 0. And so, like a lot of systems before it, Chez scheme uses tagging in order to determine its types. And so we get 3 tag bits out of the system. And we're just going to represent those. That gives us 8 tags that we can represent. We'll just use that to represent all of our types. OK, so we have a few too many types in the system to just use the type tags to determine these things. But let's first talk about how we use our primary type tags and how we allocate them. So the Fixnum representation uses the very first one of our type tags, 000. And on a 64-bit platform, this gives us a 61-bit Fixnum. And on a 32-bit system, this would give us a 29-bit Fixnum. And the cool thing on the 64-bit machine is that if I think about this as I'm going to use these things to index into things like vectors, well, this fact that I incremented my Fixnum by 1 means that I'm now pointing to the exact correct address as I move through the space, because every time I increase by 1, I'm pointing to the right thing in memory. But that doesn't work out here for the 32-bit one, because now I'm skipping over words. And so we steal one of our other type tags, and we actually have a 30-bit Fixnum, and we use 100 as our other type tag for Fixnums. And the other cool thing that works out, and the reason why we like to have the zeros down at the bottom, is that if I'm doing logical operators, I'm just multiplying, right? This is just adding a multiply in these cases to the value I'm trying to represent. And the cool thing about that is that if I'm doing logical operators, it just works out, it preserves the tagging. So if I'm doing AND or XOR, I can use the machine's version of that. If I give it 2 tagged operands, I get a tagged result out. And this also works for plus and minus, so I can just use the machine's plus and minus when I'm implementing these things, and I get the correct result out again. Now, it doesn't work out for everything. Multiply and divide, for instance. In the case of multiply, of course, 4x times 4y is not 4z. It's 16z. And so we would end up double tagging things, and in the case of divide, we end up eliminating the tag. And so we have to do some adjustments there. Of course, Chez scheme wanting to leave nothing on the table. If we see that one of our 2 arguments to a multiply is a constant, then we just don't adjust it, right? And so it doesn't have to do the adjustment at runtime, it does the adjustment at compile time. Okay, so 2 of our tags are used. We've got 6 tags left. How are we going to use them? So we have some other immediate values that we want to represent. And so we're going to use one of our other tags for the other kinds of immediates in the system. So Fixnums are sort of immediate, and that we're not going to look off at memory in order to figure out what their value is. And so we represent booleans, null, void, blip, black hole, some other internal things, as well as characters as our immediates. And you might look at that and go, well, then how do I know when I have a character and not something else? Well, of course, we just extend the tag out. And so we use the bottom 8 bits for the tag in our immediates to determine what the difference in the types are. And I'll show a little bit of that a little bit later. The nice thing about this is that it means that even on a 32-bit machine, if I've burned my bottom byte, I still have 24 bits left to represent my characters, and that's enough to represent Unicode, so I'm all set for my characters. Now, another one of our tags is used for flownums. Again, I said that we align to a 64-bit partially because of our flownums, and if we didn't give it a primary tag, we'd have to store some type information up there, and we'd end up making our flownums take up twice as much space. So we don't want to do that. So we put one of our primary type tags for flownums. Another one is pairs, for the same reason in some ways, right? So pairs is 2 words in the system, so we don't want to have extra information up there that would cause us to have to pad that out. And of course, pairs are a pretty common type in Scheme and Lisp, so it makes sense for us to do that. Symbols are another one of our primary types. So we use symbols for all kinds of things inside Chez scheme, including figuring out what function should be called when you call cons or car or things like that. If we haven't been able to compile it down because we knew what it was otherwise, then we reference it through the symbol. So if you have deeply nested functions, anything that was sort of globally bound, which is what happens when you have a symbol, or exported by a library, is going to be bound to the symbol and not in your closure. So your closure doesn't get huge as you're going through nested functions. And then one of our other primary type tags here is used for procedures. Again, procedures, pretty common. We also want function call to be fast. So if we're doing checking on whether or not we have a procedure, then we want to be able to just look at it, know that it's a procedure, and go off and call the appropriate function. And of course, everything else falls under this last tag. So what is everything else? Well, everything else has to store 2 or 3 pieces of information, right? It needs its type information. It needs the value or the data that it represents. And in some cases, we need some additional metadata. So if you think about things like vectors, byte vectors, strings, big nums, they have a length associated with them, which is how big this object is. And so we need to store that someplace. Also for things like records, where we have the record system can actually inspect the record and figure out what its structure is, we need to store that kind of information with this. Of course, we don't want to actually burn 2 words to store the type and the metadata, and we already have tags, so why not just use the same trick all over again? And so our type and metadata is also tagged. And so you can see that vectors here use 0, 0, and on the 32-bit machine, 1, 0, 0. And if you're thinking that corresponds to fixed nums, you're right, it corresponds to fixed nums. So if you look at the first cell of a typed object and it's a fixed num, you know it's a vector. At some point, until fairly recently, that fixed num was just the thing that represented the length of the thing. Some of the racket on CS changes have added immutability to the system. And so we now have an extra bit of the fixed num that's used for indicating whether it's mutable or immutable. Which I will say, I was a little tired putting slides together, and I was looking at this and I was like, this is not the number I should be seeing here. And then I was like, oh wait, no, I know why this number is here. One of the other things you might notice is that we're even careful about how we try and lay these tags out for things like our numbers. So we have lots of other number types that don't fit in our bottom. We have big nums, rational numbers, inexact, which is complex numbers, and exact complex numbers. But we have number question mark, and number question mark, we don't want it to ask about all of these things, of course. We just give a common tag to our numbers, and then we ask, is it a fixed num, is it a flow num, is it an other number, and we're done. Now, big nums continue to extend our tag up here so that we end up with positive big nums and negative big nums. We don't have to look at the whole thing to figure out if it's a big num, but the actual value of a big num is stored as an absolute value, so we differentiate the positive and the negative from that. And all of these tags that are for things that have a length, like vectors and byte vectors and strings and these other things, they all use the upper part of their bit space to represent their lengths. And so it does mean that we have some limitations on our lengths, but up until the addition of the immutability, that vectors could actually reference half of your addressable space, and now they can represent a quarter of your addressable space. And if you're on a 64-bit machine, you probably don't actually have a quarter of your addressable space. And even if you did, I don't think most of the Intel chips can map it. So I think we're probably okay for the most part. The byte vectors do suffer a little bit because they're a measure in the number of bytes. With that, I'd like to talk a little bit about some of our object representations. When we look at our object here, we can see it's an immediate because the bottom tag here is 110. And then we know it's a character because the next 5 bits up are 00010. And we don't have to look any further. We know what the type of this thing is. Of course, if we were actually asking, is this thing a character, we wouldn't take it apart piecemeal. We'd just mask off the bottom 8 bits, compare it with the thing, with the type tag here, and know whether or not it was. For our pair, again, we know it's a pair because it has this 1 offset. Now, note that it doesn't point to the start of the pair in memory because of the 1 offset. It points 1 off from the start of the pair in memory. And like the T system before it, it just computes when the compiler is run what the offset for car should be, which is -1, and what the offset for the cdr should be, which is +7 if I'm on a 64-bit machine. And so we're not doing any sort of get the original pointer back and figure out where it is. It just knows what those offsets should be. And vectors are the same way. Vectors, we have a pointer to the end of the first word, and we look at the end of the first word, or we look at the beginning of the first word to figure out what our actual type is here. And so one of the things that's kind of interesting and that cemented for me as I was putting all this together is that if I just had some random pointer off into the memory space, which is something that the garbage collector might have, and I was looking at these things, I wouldn't know what type of a thing this was, because this could have been a vector if the first item was a fixed num. It could have been some other type. So long as these things are putters in memory, we really can't differentiate what they are without having our tags down here. So I mentioned symbols are a pretty important part of our system. We make pretty heavy use of symbols. So our symbols here are a fairly large structure, a 6-slot structure. Of course, we have name in our symbol, and that's kind of what they represent. We have values in our symbol, and that's whatever value has been assigned to this thing. So if it was a top-level bound value, we can set that value, we can get that value. We also have another field for value, which is our procedure value, which I'll talk a little bit more about why we have this additional field in there in a moment. Chez Scheme has had support for Lisp-style property lists for a long time, and in fact, we make use of them internally. So there is a user-level property list, which you can use getProp and setProp on, but we also have a system property list that we use for storing things like, oh, did this come out of a library, and other information like that. And finally, we have a hash. And we have the hash in there because we store all of these things in an oblist. And as you add more symbols to the system, sometimes the oblist needs to be resized. We don't want to recompute this hash, and so we just stick the hash here. Also, because we are double word aligned, if we had just the 5 items in there, we would have padding space here anyway. So why not use it and put the hash in there? So the procedure value field is kind of interesting. It starts out pointing to this thing called the non-procedure code. And we have this procedure value here so that when someone calls something based on a symbol, we can go straight off and execute it. But the first time it's called, we have this little bit of dispatch code. Now, this isn't actually the code that's there, because the actual code that's there is a little bit of handwritten assembly inside of our, well, a high level of assembly written inside of our compiler. But this is sort of the moral equivalent. So basically what the non-procedure code does is it takes a symbol and the arguments that were passed to the function. It looks at the symbol value to figure out if that symbol value is a procedure. If it is a procedure, it overwrites the field so that the next time we come back here, not only is it not pointing to this function, it's actually pointing directly to the code pointer of the thing that it's going to run, so that when we get ready to run this thing, it's merely an offset into the symbol, and then we're off and running. If it doesn't find that there, then we have an out-of-line exception that gets raised through looking at the symbol and figuring out whether that symbol is not applicable because it was unbound, or because the value that was there that it's bound to is not a procedure. And then finally, if we didn't raise an exception, we come down here and apply the function. It gets the result. And there's sort of a performance assumption built into this, in that when you set a value, it simply replaces whatever was in the procedure value field with the non-procedure code. It doesn't look at the value that you're replacing it with to try and figure out what it should be. We want setting the value to be relatively fast, and the thinking there is that, well, you're probably not going to set the value more than you call the value. And if you set the value more than you call the value, then we don't want to pay for having to set the procedure value if you didn't even bother calling it in between. So there's a little bit of guessing as to how your program is going to work out. But that's sort of the idea behind this. Now, the other thing that we make pretty heavy use of throughout the system is generated symbols. And Chez Scheme has a textual representation of generated symbols. You can actually write this into your program, and it will forever and ever be this generated symbol. And it basically consists of 2 parts. There's a pretty name and a unique name. But we want our generated symbols to be as quick to generate as possible. So we have a structure for our generated symbols that matches our symbol structure over here. So it's got all the same fields in it. But when you create a GenSim, the name and the hash field are treated a little specially. So if I call just straight up GenSim, which is how I got this value up at the top of the screen, it puts a false in for the name and a false in for the hash. And this GenSim is not put on the oblist because, I mean, how would you get at it anyway? We can't talk about it. It doesn't have a name. And you can't give it a hash because, again, it doesn't have a name, so it doesn't have a hash. So if you use this GenSim in your program and you never print it and you never try and do something, ask about its name, it will never get a name, and it can be garbage collected and thrown away just like everything else, which is something that can't happen when it's on the oblist because we don't know that you won't try and ask for it again. If you give it a pretty name, we still don't fill out the name completely. We actually put a pair in for the name. where the first element of the pair represents the unique part of the name, and the second part represents the pretty part of the name. Obviously, we can't just put the pretty part of the name in here, because then we wouldn't be able to differentiate it from all the other symbols in the system, which just have the name in there. And the hash is, again, left blank. So I mentioned that writing these things is sort of the forcing function, but there are a couple of different pieces of the forcing function. If you call symbol arrow string, it will generate the pretty name and nothing else. And so it does the minimum work that it has to do to make this work at all. If you call GenSim arrow unique name, and unfortunately I should have updated this because I realized after the fact, it turns out, as a side note, that it's really, really hard to look at the contents of a GenSim without mutating it if you aren't just poking at the internals of the system, because the entire system is designed to make sure that it can't happen that you look at this thing and those things are false, right? It turns out that there are some little bits of hackery that you can do inside Chez to get at these things without setting them, but it is truly hackery. So if you ask for the GenSim arrow unique name, it actually sets the name and it sets the hash and it interns it. And the same is true for the symbol hash. So if it finds any of these values aren't set, it sets all these values and computes a hash, interns it into the hash table at that point. And sort of the final piece of all of this is, so where does this unique name come from anyway, right? So we used to have an internal system that would do this, but someone rightly noted that it exposed the machine and the time that it was created as part of if you knew what the representation was, and for security reasons, that's probably a bad idea. So we now use a UUID generation depending on what operating system you're sitting on. We have a library if it doesn't provide one. We generate this symbol the first time we ever need to figure out the name of a GenSim. And it gets generated once for the session, and it maintains it throughout the session. So every GenSim that I created in this particular session, which of course I won't be able to get to ever again, because it will generate a new UUID the next time I start up my session. It generates this uniquely at the first time it prints, and it then just assigns an index to it. One of the cool side effects of not doing this until you get to the end and want to print these things is that if you are, for instance, looking at the output of the expander, or you have some use where you're compiling things and generating GenSims, the GenSims come out in printed order in the program. So you end up with 0, 1, 2, 3, 4, 5 through the program, and it actually is surprising how much easier it makes it to read, as opposed to just some random numbers. And every once in a while I screw myself up by asking about one of these things in the middle, and then when I go through looking at code, it's just this random number is at the start of all of these things instead of 0. So, but with that, I'd like to talk about some of our other small optimizations. So I talked about at the beginning one of the ones that I think is particularly cute. One of the other things that we do is strength reduction. This is a pretty common thing for compilers to do, and especially for things like multiply and divide. And of course, Chez does this for multiply and divide too, but they're not very interesting. But Scheme has this kind of interesting strength reduction for the equality operators. So there are 3 equality operators that sort of have increasing strength: EQ question mark, EQV question mark, and equal question mark. And for increasing strength, I mean both that they can compare a larger class of things and get the equivalence, and also they take longer to perform. And of course, to some extent on the compiler side, we care most about the fact that they take more time to perform. So whenever we can do EQ question mark, we'd prefer to do that. We also have membership operators that are based on these, so MemQ, MemV, and Member. And so we strength reduce, obviously we don't strength reduce EQ and MemQ because they are the strength reduced target, but we strength reduce these 4. So to talk about the equivalence ones first, for EQV, if we have either argument as a constant, we look at that constant and figure out if it's EQable. Well, what does it mean to be EQable in our system? Because EQ is actually a system-dependent kind of thing. Well, for us, it's pointer equivalence. So we know that symbols are EQ, because that's part of the definition of a symbol. And we know that things like our fixed nums and immediates are EQ. So where on other systems it might not be safe to compare your fixed nums with EQ, it is on Chez just because of our representation. And so we want to make sure that if you call EQV, especially because we tell people if they're comparing things like this that they should call EQV because it's semantically the more correct thing to do, we don't want to generate worse code because you did the right thing. So we make sure to turn that into the right thing. Equals a tad more complicated. It does the same thing in the obvious case. It figures out whether you have an EQable or an EQVable constant. But it actually works just a little bit harder. And it says, if the thing that you handed me as your constant was a pair, as opposed to an EQable or an EQVable constant, where a pair is not, then look inside that pair and recur through the elements of that pair to see if I can completely get rid of this call to equal by turning it into a series of ands and comparisons with EQ or EQV. So it gets bored doing this pretty quickly because we don't want to generate unbounded amounts of code here, and you really can. Especially if you didn't have something in there that checked to make sure that this wasn't circular. But we go like 3-4 levels deep, and then we give up. And if we can't find that we've got EQ or EQable things at the bottom, forget about it. And of course, if the second element was constant, we just throw it through the same function, reversing the arguments. Now, I didn't say this earlier, but I meant to, which is that if these are both constant, well, we don't expect to see this here because some other part of the compiler should have already eliminated it, right? We should never see both of these things being constant. So we do a similar transformation with MemV and MemQ. So MemQ, the first element we look at, if it's EQable, well, then we just generate MemQ. But of course, the second element is not going to be EQable because we know it's a list, right? It should be a list. And so what we do instead is we look through the constant list and see if it only contains EQable elements. And if it's only EQable elements, then we'll generate the MemQ. We do a similar thing for member. Look at the first element. If it allows us to say MemQ or MemV, we do. Or look at the second element. If it's a list, go ahead and do the MemQ or the MemV. Now, MemQ and MemV, we do other special things with. So MemQ and MemV, if we happen to see that this is a constant list, a constant pair, I should say, then we actually will also do the expansion through this and unroll this down to EQs or EQVs as is appropriate. And you might wonder, why have we spent so much time on member and MemQ and trying to make these things fast and not, for instance, on things like the association list handlers? Well, part of the reason for this is that in Chez scheme, case expands to member ? And we want the expressiveness of member ? Which actually, if you are just importing the R6RS library, you won't get because R6RS says it has to be memv. So we wanted it to be member. If you put something in there that is some big hairy object, but it's a constant object, well, that's okay. It just does the equal check on it. But if you don't do that, if you're putting in there fixnums or symbols or things that are fairly common to use in case, well, we don't want you to pay for the fact that we decided to use member. And so we sort of handle that here. A related optimization that we do, in that it's related to equality, are our length relational operators. And so this is basically a recognition that sometimes I want to call length on something, and I know that I'm comparing it to some small integer value. And by golly, it would be nice if this was just a constant time operation instead of being a linear time operation on the length of the list. And so when we see something that looks like this, we will go through this process and say, okay, well, if it's 0, obviously I just meant null ? And if it's 1, then, well, it shouldn't be null, but its could or should be null. And if it's 2, then it shouldn't be null, and its could or shouldn't be null, but that could or should be null. That one, the second one's could or should be null, and so on. And we do this out to a length of about 4. And we do this for kind of everything. But even in some cases where it's sort of pointless, like who says negative length of something, right? It's obviously always false. And so this just turns into false. But it's sort of a funny thing, right? But yeah, it's all these things. So now the downside of all of this is that this only works at optimize level 3, which is our don't check the types. And if you noticed when I was talking about this, I said we make sure that the thing is not null. Well, not null doesn't tell you that it's a pair, and then we go off and call cdr on it. So gosh darn it better be a pair, because if it isn't, bad things are going to happen. This is where you run into non-recoverable memory failures, or at the very least memory failures, because you just tried to take the cdr of something that is who knows what. And so we only do that in this case. Now we could check pair ? And go off to some error condition when we knew it wasn't going to be a pair, but that just bloats the code and generates more code and all this kind of stuff. So we only do this at optimize level 3, and we only do it to a certain depth. And unfortunately, this makes it a bit of an attractive hazard. So if I am routinely passing a list of 1 million items around, and I'm relying on this thing to fix that for me so that I don't have to worry about the fact that I'm passing a list of 1 million items around, and I started out going, okay, I'm going to compare it with 1, 2, 3, maybe even 4, I think. And then I'm like, oh, I need one more case. The lists that are 5 long, suddenly my constant time operation just blew up into this, operation n over this gigantic list. So that's kind of a bummer. The other thing is that we wish, that it would work on things like case. So I'd like to be able to say case length of this thing, and if it's 0, do this, and if it's 1, do that. But that also doesn't work because we don't have things in the right shape to see this pattern at that point. And so it's a bit of an attractive hazard. And it's also a bit of a slippery slope. You start going down this road, and I think it probably was just equal to begin with. And then it was like, well, it might as well be all the equality operators. And then it was like, well, why not the inequality operators? And then you end up with something where it still doesn't do quite everything you wanted it to do, but it does enough stuff that you want it to do that you're probably not going to get rid of it, even though it kind of also doesn't fit Chez scheme's mythos in that you want performance to be predictable. This sort of gives you a little bit of a unpredictability because you have this little hockey stick of things were working out great until I accidentally made my number too big, compiled it at the wrong optimization level. So it's kind of a bit of a bummer, but it's really syntactically cute, and so we probably won't get rid of it.
It's a shift in algorithmic class.
It is.
It's not just a little bump.
Oh yeah, that's why I said hockey stick. Hockey stick goes
okay.
thump, thump. So yes, it's a change in algorithmic class. Yes.
For example, in length.
Yes. Yep. Yeah. So it's kind of a bummer.
Or diversion.
Yeah. Yeah. So length will survive circular lists and things like that, but so you're not going to diverge. But yeah. So sorry, did you?
That was the question.
Oh, okay. Yeah. So another thing that we do is we look for things like repeated Fixnum checks. So if you call Fixnum on a bunch of different stuff, it looks at the fact that it's calling it on Fixnum, and it says, I'd rather not have a bunch of branches that I generate in my code. I'd rather just have one branch. And because our representation allows us to preserve the fact that it was a Fixnum across OR, we just OR them all together, and then we call Fixnum ? On the result. And that's great. We get to do this neat little trick here, and it's because of our representation, but it's also kind of a pattern-based thing. So if you put any code, if there was any code in this ... that wasn't a Fixnum ? of a thing, yeah, it just gives up at that point. It says, well, I've got this small list, and I can do it for the small list. Maybe it's got another small list on the other side, but it can't bridge the gap. And part of that is because it turns out that, you have to do more work to bridge the gap, right? More work other than just looking a little bit further ahead. You have to make sure that that thing wouldn't interfere with the next set, that you're allowed to basically reorder and not change the semantics of the program.
Is that because of mutability,
or? It's partially because of mutability. It also could be that someone calls error off here, or some other sort of side effect happens early. Or of course, we're in a language with call CC. So if one of these expressions, right? I wrote this slide wrong. These should be expressions. If one of these expressions was doing something with call CC, well, who knows, right? I mean, you change the observability of the rest of the program when you have your hands on the continuation. And so you have to be careful that you don't do something that allows people to see, doesn't allow you to see what's happening behind the curtain, right? The whole goal of optimization, as Kent likes to say, is cheating and not getting caught. And call CC means that you kind of get caught in a lot of cases if you aren't really careful. So another thing that we do is direct call optimization. So if I have a letrec that binds this variable, and the variable isn't mutable, right? Or isn't mutated, I should say. Obviously, all the variables are mutable. But if we've looked through the program and we've seen that you're not going to mutate f, then we really know what the value of f is here. However, naively, this is creating a closure. And within that closure, the first element is a pointer off to code. And so what we would have to do is say the thing that we're actually applying here is an offset through that closure to figure out where the code is, and then run the code. And then additionally, we have to pass the closure along to it in order to do this. Now, I've represented it as an extra argument here. Chez scheme actually doesn't do it as an extra argument. There's a register that passes this stuff, but it's morally equivalent. We have an extra argument that is passed if we need the closure. So because we can sort of, from the syntax of the program, see what f is here. We know we're within its binding site. We can just go ahead and look up what that f is. It's worth noting that by this point in the compiler, all of our variables are unique, so we never have to worry about even screwing up the scoping. But we know that this unique variable is here, and we know that we're going to give lambda a direct call label, which is what DCL stands for. So we're just going to take the direct call label of f and we're going to put it right in the code, right? So that it's actually there when we're ready to call this function. So we can jump straight off to it. This is what Kent likes to refer to as being not stupid. So he doesn't want the compiler to generate code that is obviously stupid to generate. And so he wants the compiler to be not stupid. And this is one of the things that falls into the be not stupid category. This pays off really big dividends in the case of case lambda. And of course, what I haven't told you is that the case of is always the case of case lambda, because at this point in the compiler, there is no lambda. There is only case lambda. So in the case of case lambda, we have the same situation, right? We would call off to this procedure code. We could do the same trick. We could just put a label in here, which is the label for our entry point. We'd have to set our argument, the number of arguments that we're passing when we do that, because this label here doesn't just jump into some one of these bodies, right? It wouldn't know which one to jump into. It's actually a little dispatch that looks at what the argument count is, and then based on the argument count, decides which of the bodies it needs to execute. In addition, for things that have rest arguments, it actually needs to take the arguments that were passed out of the argument passing registers and stack frame locations, allocate a list to put them in, and put them in that list. And it can't know the length of the list ahead of time because it doesn't know what's going to be called with this function. So we really don't want to do those labels, but we already know that there are going to be labels for each of those within the body of this thing. So we just skip past that entirely, and we just jump directly into the bodies, which is kind of nice, actually, because it means that, I never think about this when I'm writing my functions because I just know that Chez scheme is going to take care of it for me. So the other trick that we can play here is that because we know that this is going to be a rest arg, because there's knowledge about what I'm calling, I can go ahead and create the list here, and now the list can be allocated statically because I know I can figure out what the allocation is statically, I should say. We don't allocate it until runtime, but I can figure out what the allocation is statically. I can allocate that as one big block and just fill it up, boom, 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 with the values that get computed here. Now, there's something not quite right about this function call. Does anybody recognize what might go wrong with this?
Could overlap stuff too.
Yeah, that was my
It might match one of the other ones, but we're sort of done with the matching at this point. So the thing that goes wrong is something that I mentioned earlier, which is that we are in a language with call CC. And we are in a language with call CC that also doesn't specify the order of evaluation of our arguments. And so if E1 isn't evaluated before list E2 blah, 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 then it had like someone had grabbed a continuation and that it could observe the observation, it could observe the allocation rather of the list. And we don't want that to happen, right? We want to make sure that this looks exactly like it would have looked otherwise. And so we actually have to let bind the E1 outside. And if we had any other arguments that weren't inside that list, of course, E2 through EN are fine because list is applicative order. It's just going to evaluate them before it actually allocates list. We just have to be a little bit careful about how we do these things. And this all sort of falls in the be not stupid category. We also recognize let forms. So I'm so glad that someone earlier talked about how let expands into lambda, because you won't be surprised to hear that in Chez scheme, it does exactly that. We have a let macro and it expands into this direct application of lambda. And through the first part of the compiler, it's treated exactly this way, just direct application of a lambda. But at some point in the compiler, we no longer want that to be a different thing than let. We actually want to manifest the let. And we do that because we don't want the overhead of having to allocate a closure, and we don't want the overhead of having to do a function call. And we want to expose x1 through xn here as local variables that the register allocator has an opportunity to put into registers, or and if not, stack frame locations, which is still better than having to pull them all off an argument list and put them somewhere. So we want to have this form, and we don't do this in quite the same pass, but there's an earlier pass that makes sure that this actually looks like that, because of course, as I said earlier, there is no lambda, there is only case lambda. So a case lambda with one body that matches its arguments is turned into this. This is also a be not stupid thing, right? No need to have these things that are obviously local variables be not local variables. Another thing that we do when we recognize let is we recognize certain special cases of let rec. So for those of you who have written the let macro, you might recognize this as the expansion for named let. So named let binds the function that the let would create in the name. And we have to expand into this because if we didn't, we might accidentally capture the name variable because it was introduced by the user, just like everything else within there. So we want to make sure that we don't accidentally capture it. But it turns out for some later things that we're going to do, this is an inconvenient form for us to have this. And so when we see something that looks like this, we translate it into that, which basically just pushes the call within the body of the let rec. And you might look at this and go, that seems like small benefit. Why do you bother doing that? And the answer is actually to expose loops. And so when we see something that looks like this, which I've just expanded our E out into the lambda that exists there, then we will try and make this into a loop because we don't want to tail call a function. Again, we would rather not allocate the closure. We'd rather have these things be local variables, and we'd rather not have the overhead of the function call. And so when we see something like this, we treat it like it was a loop, and then we analyze the body to figure out if it really is a loop. So when is it a loop? Well, we assume optimistically that it is a loop because, of course, you always want to be optimistic. And then we look through the body and we try and figure out whether the function that we saw bound there is always called in a tail context. So if we see that the function was returned or put into a data structure or passed to another function, or it's called but not in a tail position, then all of those things we give up, we generate the code that was there. Otherwise, we generate a loop out of this thing. And there's also benefit, or at least there has been in the past, benefit to matching the chip's expectations around the kind of code you're going to generate, and exposing the loop to the chip is also useful. And we can actually do this with nested loops. So if you have big nested loop constructs, it just sort of keeps track of which things it's trying to make sure are a loop. And as long as they're only ever called in tail call position, it will generate a loop for you. So the last thing I'm going to talk about is basic blocks. So Chez scheme, like a lot of other compilers, eventually ends up in a form where things are represented as basic blocks. And a basic block is basically straight line code that at the end either goes to a single other piece of code or branches and goes to one of two other pieces of code. So I might have a very high in degree, but I only ever have an out degree of one or two. I suppose 0 in some cases if we're going to an error condition. So the first thing that we want to do is we want to look for blocks that look like this. They just contain a goto in them. That's the entire body of the block. And these are basically just what we call repeater blocks, right? They are a jump to a jump. And we'd never want to generate jumps to jumps because why would you do that? That would just be a silly thing to do. And so we want to eliminate all of our jumps to jumps. And so we do just that. We just throw the jump to jump away and we sort of path shorten the code and we put the final destination in as the jump point in there. But we still have the problem that we have a graph structure here and we need to lay it out linearly in memory. We could lay it out in memory however we want, right? Because we have labels and we have goto, so we can get from one of these things to any of these other things. That's really not the problem. The problem is that it can be of benefit for us to have a common path through this. So we need to figure out how we're going to prioritize our blocks here. And so what we do is we mark some of our blocks as pariahs. And a pariah block is basically a block that is the result of some error check because of our type checking. It could be because it's less commonly called code. So for instance, in our allocation system, we have a quick allocation, which is basically bump the allocation pointer and see if it's still within our allocation space. So we hope that that's what's happening most of the time, and I think it probably is what's happening most of the time. In fact, I'm sure Kent probably knows whether it's what's happening most of the time, but that's how we handle those. And then in the cases where that doesn't, where we have exceeded our point, we have to go off and do a much more expensive call to our storage system to have it allocate a new allocation space for us. So that might be how I get a block like this that goes from the common code and comes back to the common code. If a user calls an exception or raises an exception, that causes it to be a pariah. And then we also have a form in the language now, which allows you, the scheme code writer, to say this block of code is a pariah, right? I expect this to not be on my common path. Please organize it appropriately. And so what we end up doing then is we sort of sort by jumps all of our code together in one big long list. And unfortunately, I ran out of space to do it all in one big long list. But imagine this is one big flat list. And then our common path is loaded at the beginning, and our less common path is loaded at the end. And even if this is a very big function, it's at least more likely that our straight line code will end up in the instruction cache, which is where we want it, where we can get to it quickly. And our less common code, which is often going to go off to some error or something like that, is not in there. And so if we need to go off and retrieve that code, we can go off and retrieve that code and call it then. One of the other kind of interesting things to note now is that if you call error in like somewhere in the middle of a longer string of code, it will not treat it as a non-tail call anymore, unless you set the debug level to tell it it's not a tail call, because Chez scheme looks at that error and it's like, well, I know I'm not coming back from that, and so it just treats the rest of the code as dead and turns that into a tail call, even though it may have come in as a non-tail call. Although you can set it to preserve that. And you might want to set it to preserve that because, as it turns out, if you went down one of those error paths and you go looking back to see what caused the function, you might want to know where you came from. And you won't know where you came from if you don't have that in there. So there is a debugger setting for that. So with that, I'm on to my summary, which is, sweat the small stuff, right? It's important that we treat the small stuff in the program as just as important as like the big optimizations like CP0, which does our inlining and a bunch of other stuff at this point. But making function call faster makes every program faster, right? So if you can make function call faster, every program benefits from that. Not every program is going to benefit from some of the other optimizations in the system, which isn't to say that those optimizations aren't still important. It just means that if you haven't spent the time to do the small stuff fast, then you're going to derive less benefit from getting the big stuff right. But maybe don't sweat too hard. I think our length relational operators is a good example of where we maybe sweat a little bit too hard. We push that not quite as far as we would like, but farther than maybe was logically should have. And so, there is some things in here where we might want to be a little bit thoughtful about whether or not it's worth the work. There's always room for improvement. So, I mentioned in a couple of places where we had things that were pattern-based. We would love for those things not to be pattern-based. I would love for loops to be recognizable even when you weren't just binding a single let rec, right? This single feature inside Chez scheme has caused me to write define function, let loop, and then have the loop take all of the arguments to the function and call itself again, because I know that I will get the benefit of it being a loop and not have to do the internal function calls, simply because I know that if I have a bunch of defines, they'll be put into a single let rec and it won't get this benefit otherwise. So that's kind of an unfortunate side effect of this. And in fact, as we were writing these up, I was talking to Kent about this, and he was like, oh, somebody has something for fixing this. So maybe one of these days we'll get around fixing this, and I'll stop writing let loop in all of my functions. And then the final part is that, I talked about the representation of the system, and I talked about the compiler. And one thing to keep in mind is that the compiler and the runtime system they need to work together. So the compiler needs to know what it can rely on the runtime system to do for it, and the runtime system needs to know what it can rely on the compiler to produce for it. Now, I didn't talk about garbage collection, but this is especially true for the garbage collector, right? The garbage collector needs to be aware of what the compiler did, and the compiler needs to be aware of what the garbage collector is going to do. And if you screw this up, unholy hell breaks loose, because I have done that a number of times. It's very, very sad times, and it usually means going into the GDB, which is very, very sad times when you're trying to debug into Chez scheme code, because essentially you have no tools at that point. You're looking at assembly code. So with that, thanks, and I'm happy to take questions.
Questions for our speaker?
Yeah.
Yeah, so I really like this example you gave where you talked about this question I asked basically, where you couldn't sort of reorganize across when you had these sort of interspersed calls to predicate checks for Fixnums.
Yep.
I would think that the vast majority of time, I mean, you mentioned things like effects like call CC and sepping and stuff like that, but I would think the vast majority of the time, with a little bit of analysis, probably you could be able to get in most of the cases. Does GenSim do any of that analysis? I believe it does some of it, and I'm sort of wondering, could a little bit more analysis, sort of sauce, kind of help there? Because I would really think the vast majority of the time you're doing these kinds of checks, mostly the programmer wouldn't really want, like semantically you kind of don't really want to write code like that. At least I wouldn't most of the time.
Right, so two parts of this. So Chez scheme does do, we do analysis on various things. Like I mentioned, actually, that we know whether a variable is an assigned variable or not an assigned variable. We get some benefit of analysis through the fact that we have the inliner, right? So we don't get all the benefits of doing something like a CFA, but we also don't pay the cost of doing a CFA, and so we get some benefits just from those kinds of things. But one of the rules that Kent has always had is that nothing goes into the compiler that's worse than n log n. And so some of these analyses quickly get more expensive than n log n. And if you would like an example for a very complicated thing that got even more complicated because of the n log n, Michael Adams' PhD is a great example of how he tried to push this as far as he possibly could for doing type recognition, or type recovery rather. And it's brilliant stuff, but it's also it's very dense to understand because he had to do a lot of work just to try and get that time and space bound in there. And so we not everything in Chez scheme fits that model. There are things like closure allocation that figuring out what the closures are, I should say, that can be quadratic, but that's kind of unavoidable. So there are some things that are worse than that, but for the most part, we try and keep to that.
With that specific thing, bracket on Chez, port for bracket, bracket on Chez, port for Chez scheme has a little analysis.
Okay, great.
Do you have it in the same function that it does, or the same pass that it does that?
An extra CP0.
Oh, an extra CP0 thing. Okay, yeah, that makes sense.
Because it supports some.
Yeah. CP0 has grown up to be like the warehouse of all of the sort of random, I need to do a little bit of code reordering, or I wish the record system was static, and so let's figure out how to make it as static as possible, and there's a bunch of complicated stuff in there as a result. It does mean that if you ever go wade into the code that's inside CP0, it's not easy to understand what's going on. But yeah, there's a lot of stuff in there now.
So a bunch of schemes have a function that is has this length at least that many elements, right? And it's not as fast as unrolling what you're doing, but couldn't you call that once you go beyond 4?
We don't have such a function, but you could obviously write one, yes. So yeah. I mean, we could have something like that, right? That would be. So
that would preserve your
yes.
performance continuity.
It would. That's true.
Die cache though, maybe. I mean, if you're jumping to this other function.
So I mean,
the point is not going through the million.
It'd be yeah. I mean, the thing is that it would probably be a little bit slower because the code wouldn't be in line there. You're paying the cost of the function overhead, but unlike what we do right now, it doesn't change the complexity class, right? Because the complexity class would still be based on what your n is, and not based on the length of the list. So yeah, we could do something like that.
So on the subject of maybe this was going a little bit overboard, do you have a strategy for collecting information about how often all the different things fire in the optimizer to tell whether these things actually happen in the programs that you care about? And
Right. So unfortunately, not a systematic way to do that, right? So there probably the most systematic way of doing this right now is to turn profilers on the compiler itself. And so we have as efficient as we have figured out how to make it profiling system that doesn't do, like a lot of people think of profiling as being like how much time did I spend in this function? We don't do that. What we do is per expression counts how many times did I hit this count. How many times did I hit this particular expression, right? And so we could derive some of that information from those counts after compiling it over a range of programs. But we've never really used it that way systematically. What we tend to do is that, like, when I was working on the closure optimization with Kent, we sort of built ourselves a little thing for analyzing the closure analysis to figure out, like, well, what is the average size of closure that we produce in the code we're compiling, and how often can we get away with not creating a closure or boiling the closure down to just a single item or those kinds of things. So we've not done the systematic thing. And I will say that every time I have to do one of these things, I think, God, I wish we had a systematic way of doing this. So
It might also benefit feeding back information from the optimizer to the programmer.
yeah, so actually we do some of that with the profiling stuff.
Yeah, like the feature, you could do the kind of thing that we did in Racket for the optimization coach, and say, oh, you almost hit that damn thing, but a little bit
Yeah. That is true. We don't do that.
And the same system could help you there.
Yeah. We do have now profiling feedback. This is something that I think William worked on when he was at Cisco, briefly at Cisco. So we have profiling feedback now in the system where if you're using case or we have an extended exclusive cond and you output profiling information from a run of your compiler,
Right.
you can feed that profiling information back in and it'll reorder your the clauses of your exclusive cond to give you whatever the most commonly hit one is first, and so you can try and do those things faster. But we have not done that as feedback.
People with Vincent or something, right?
Yeah.
No, it's right, I got it.
Yeah. So, yeah.
How does sweating the small stuff interact with the maintainability of the compiler? Is it all pretty clean, or are there some things that turn towards, or that would be if you tried to generalize them?
So if I may toot my own horn a little bit, the nanopass stuff actually has made a lot of this stuff easier, right? Because if you want to add an optimization now, you don't have to figure out how it fits in this big monolithic pass. I mean, one of the problems with the older Chez scheme compiler was that there were optimizations that Kent wanted to do that needed to be done after one thing and before another thing, and those two things were in the same pass. And so it was very hard to figure out how you threaded those in there. And now those two things are just different passes, and you just stick a new pass between them. And so, like, the first thing that I showed is an example of that. And it's funny because I knew we had that thing, and the idea for this talk is really old, actually. We basically, I thought this optimization that I had first is so cute that when we did this, that I was like, oh man, it's too bad this is such a tiny little thing. I can't write a paper about this or give a talk about this. It's just too tiny, but it's so cute. It's this little gem, basically, right? And so at the time we were like, well, if we ever get asked to do a keynote, we should totally pull these together and just do that as a talk. So that was sort of the inspiration for this. But I had not remembered even that it's just a single nanopass pass. And so when I went back to look for this to try and extract what exactly did we do, right? I was pleasantly surprised to see that this pass, this is its entire job. That's all it does, and it just fits into the rest of the system, and you can do these things. So that helps the maintainability certainly. And so for a lot of the primitive stuff, we have a gigantic thing that expands the primitives, and all of those are abstracted into like individual inliners for the different things. So those are also fairly straightforward to maintain, right? Even though they're all done in sort of one big pass. So go for it.
I think it's time for you to write a book. I'm serious. You have all this great information.
Yeah.
A lot of people would like.
Yes.
And it's not really small enough for a paper.
Yes.
So you should.
Small compiler.
Yeah. So Kent and I have talked about this before.
I figured.
And
Time to do it.
And if
Getting younger.
no, this is definitely true. I will say, like, the hard part is, like, we both have full-time jobs that aren't this, right? And so, it means finding time in amongst our other responsibilities, one of which is actually maintaining Chez Scheme, right? And if you look at the backlog of Chez Scheme, you might note that we have not done the best job of doing that necessarily. So, and some of that is because, I don't work on this during the day. I work on it in the evenings or on the weekends when I have time. And I am, unfortunately, as it turns out, easily distracted. So I had the joy of having somebody who was interested in doing the compiler class from IU, who lived in the RTP, which is the area that I live in. And he was like, just give me this stuff and I'll go through it. We can go through it together. And I'm like, okay. And I'm really impressed by this guy because he was doing this with a small child at home and a full-time job, and then with 2 children at home and a full-time job, 2 small children at home and a full-time job. And I don't have enough energy for even doing both my full-time job and this stuff. So, he went through the whole process. I was like, oh, this is great. I redid all the stuff to use the nanopass framework. I started rewriting some of the assignments. I was going to put all this stuff online. He finished the stuff, and I'm like, okay, I really need to finish this stuff. And then I get distracted by other shiny, interesting things, and I kind of go off and work on those. So I need someone to, like, I don't need someone to chain me to it, but I need someone to be like my foil for doing these things. Otherwise, I have a tendency to decide that I'd rather sit down and write random
There's
code.
always excuses.
Exactly.
I assure you that's true.
Exactly. So, all right.
Any more questions?
So is there an easy way to see the assembly code that's submitted, and is there tooling in Chez where if I wanted to, like, include some assembly inside of a Lambda, or what sort of things are there if I want to muck around and see actually what's being generated?
Okay, so let's see. So if you want to see what's being generated, let's see what random stuff is on my terminal here.
We can't see your terminal demo.
Oh, good. Well,
I think you want to do Control F1. Is that right? On a Mac, maybe Control F2.
I don't have function keys on here anymore. So
Right.
I guess I do somewhere, but
I think you should control.
all right. So let's make this bigger. So,
Like a Microsoft thing.
so this used to be an internal thing. In fact, it's still an internal thing, so you have to work a little bit to get at it. But it turns out that when you open source things, you can talk about all the internal parts because they're visible. So we have this syntax. Oh wow, this is not gonna show up very well, is it? Let's see if I can pick a color scheme that actually. Yeah. Yeah. So let me see.
I think this is fine.
Better-ish? No. There we go. Let me get rid of my inspector here. So if you do hash percent is the thing inside Chez Scheme that says, I'm about to tell you about a primitive. And you can do hash 2 or hash 3%, which tells you I'm going to tell you about a type checking or not type checking primitive. But I'm going to tell you about a primitive. $sign is what we've started prefixing all of our internal primitives with, but they're still available. You can still call them. So we have a primitive called assembly output.
And that lives in the obelisk, I presume?
What's that?
Does it live in the obelisk?
It gives you, does it live in?
The obelisk.
It does live in the obelisk somewhere, yes, I'm sure it does. You can give it a port here to output to, or you can just tell it true. And then after you do that, now if I, so let me show you what you might not expect to happen. So if I type in something simple, like, actually this may or may not work, we'll see. So it did do the right thing, but it did give us 3. But it used to be the case that this would just give you 3 as a result because it was running the interpreter and not the compiler. But I think we fixed it so that if you have assembly output turned on, it doesn't use the interpreter ever. So you'll get the assembly output of this thing. And we've even tried to make it a little bit prettier. Let's see. Well, let's do this the right way. Let's say hash 3% fx0 and 1 and hash 3% fx times n f hash 3% fx minus n1. Normally I just turn optimize level 3 on first because it's easier. So you will see big blocks of code. Now, one of the things worth noting is that this is not the assembly language for some real assembler, because we don't have an assembler and we don't use an assembler. So this is actually just a representation of our internals, because we generate the machine code directly. But when we're going through the process of coming up with what that machine code will be, we capture these things out. And so if you look at the very top of the screen here, you'll see f colon, which corresponds to the function that we're trying to run. And then this is actually all the labels and all the code. And because unlike Kent, I can't do all the computations in my head, I actually made sure that we actually put the labels in where we're jumping. So we print the labels of where it is that we're jumping to and not just the offset of where we are jumping to, because my feeble brain can't do all of that in my head. And then usually if you're defining a function, you'll also see something like this DCL blah, 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 blah. This is the anonymous function, which was the wrapper for compiling and setting the top level symbol. So most of the time this is just stuff to ignore, but you can definitely see this. And you can also turn this on before you compile a library or compile whatever else, and it will generate for you code like this. And we use it ourselves when we're debugging Chez scheme to generate assembly, which is super helpful if you do find yourself in the awful situation where you have to go into GDB to debug something. So, yep.
Do we have any other questions for our speaker? All right, let's think one more time.
Thanks very much.
Awesome.